Hey guys, up until now we've learned a lot of different ways that we can integrate. Unfortunately, as it turns out, there are a lot of functions that you can't integrate using the methods that we've talked about. So as one example, let's say we had the integral from 0 to 2 of e to the x squared dx. So unfortunately, u substitution won't work. Partial fractions isn't going to work. Trigonometric substitution isn't going to work. Nothing's going to work on this guy. That being the case, we need to resort to approximating techniques. So you've actually already learned a couple of approximating techniques, the left sum and the right sum, several lectures ago. But I'd like to review those and talk a little bit more about them. And then I'll introduce two new techniques, the midpoint rule and the trapezoid rule, as alternatives. So the first thing that I'd like to do is with n equals 2, I want you to approximate this integral using the left sum and the right sum. Again, this is review for you, so give it a shot, pause the video, and then press play for the solution. All right, so hopefully you drew a picture to help give you an idea as to what e to the x squared looks like. E to the 0 squared is just e to the 0, which is 1. And e to the 2 squared is e to the 4th. This guy is just going to look like this. And if we go from 0 to 2, then that's what that will look like. So if we do a left sum, and we break this into two subintervals, then we're going to use this height as the height of the approximating rectangle. And we're going to use this height as the height of the second approximating rectangle. Again, all I do is I go to the leftmost endpoint of each subinterval and use that guy as the height of the rectangle. So it looks like for my left sum, the height of this is going to be e to the 0 squared times the width, which is just 1, plus e to the 1 squared times the width of that, which is 1. And looking at this picture, I can see that I'm going to get an underestimate. And the reason for that is the curve is above my rectangles. So this guy is an underestimate. All right, let's play the same game with a right sum. So let me get rid of these rectangles. So for the right sum, I'm going to go to the rightmost endpoint of the interval. Go to the rightmost endpoint of the interval. And let's see what happens here. Well, now my first height is going to be e to the 1 squared times 1, that's the width, plus e to the 2 squared times 1, that's the width there. So that'll be my approximation. And again, just looking at the picture, I see we have an overestimate. So I guess then, if f of x increases on the interval a to b, then the integral from a to b of f of x dx is going to be as follows. So let's see, this guy's increasing. I'm always taking the larger value of the two. So I guess the right sum is going to be larger, and the left sum is going to be smaller. This is one of those things that you don't want to memorize. All you need to do is draw a picture, and it will clearly show you whether the left sum or the right sum will be larger or smaller. And I'll leave it to you guys to convince yourselves what happens if it decreases on the interval. If you draw your picture, you'll see that this is the case. The right sum estimate is going to be lower or less than the integral, which is going to be less than the left sum estimate. And just to think about this intuitively, f of x is decreasing. So if I use the left sum, I'm using the larger of the values always. So that's why it's going to be an overestimate. If I use the right sum, then it's going to be an underestimate because I'm always using the smallest value on the interval. So again, that was just review, but I want to be clear that left sum, right sum, those are pretty arbitrary. I can actually do any sum that I want. So for example, I could call the, let me call it the Eric sum. I'm going to go 90% of the way through the interval, and I'm going to use that guy here. 90% of the way in the interval and use that height there. You can use any point that you want. In fact, there's a proof, much more advanced than this class is up to, but there's a proof which basically says, hey, you can pick any point you want, and you'll always get the area, the true area, once you take the limit. And that should make sense intuitively because these rectangles are smushing together so that whether I use this 90% rule or the left sum or the right sum, those points are becoming arbitrarily close. Well, the one that I do want to study, is an official rule as opposed to the Eric rule, and that's called the midpoint rule. So let's take a look at that guy. So this is another way that I can do the sum. And basically, the name says it all. So here's 1, here's 2. You're literally going to go to the midpoint of the interval and use that as your approximation. You're literally going to go to the midpoint of the interval and you're going to use that height to develop your rectangle. So what would that look like then? Well, stop the video for a second, see if you can figure that out in terms of approximating the area. Right, hopefully you said that I'm now going to use e to the 1/2 squared times 1, because that's where this value is. And then plus e to the 3/2 squared, once again, times 1. In other words, 1.5. So that would be another way of approximating. The final way that I want to talk about is related to the midpoint rule. In other words, the left sum and the right sum are related in terms of whether a function is increasing or decreasing and whether we get an overestimate or underestimate. Well, the midpoint rule is related to something called the trapezoid rule and another feature of the graph. So let me introduce that. So let me keep this up here so we can take a peek at it later. So the trapezoid rule, once again, does pretty much what it says it's going to do. So what we're going to do is we're going to draw trapezoids. So instead of a rectangle, what I'll do is I'll connect here and then draw a straight line back. So up here and then a straight line back. Well, as straight as it goes. So that's a trapezoid, and that guy's a trapezoid. So hopefully you realize that that looks like a really close fit to the curve that I drew. So the question then becomes, what is the formula for this? And what I'd like to do is derive that. So instead of using 1 and 2, let me call this guy x sub I and this guy x sub I plus 1. And my goal right now is to find the area of the ith trapezoid. Then all we need to do is just add those guys up. So maybe you know the area formula for the trapezoid, but let's look at this using first principles. In other words, let's look at some shapes that we're hopefully much more familiar with, which in this case would be a triangle and a rectangle. So what is the area of this rectangle? What is the area of this triangle? So I'll give you a minute to try that by yourself, and then you can take a look at the derivation. Hint, I'm going to call this function f of x. Give that a shot. All right, so hopefully you said, well, this rectangle has a height over here of f of x sub I. So it's going to be f of x sub I times this distance. Well, this distance is x sub I plus 1 minus x sub I, and we've given that a special name in the course, namely delta x. So that's that guy. Plus, we need the base of this rectangle, So the base of the rectangle is delta x times the height of the rectangle. So how do we get the height of that rectangle? I'm sorry, height of that triangle. So we want this guy. Well, this total distance is f of x sub I plus 1. That's this whole distance. This whole distance is f of x sub I. So can I just subtract those two to get that distance that I'm interested in? Yeah, I think I can. Well, that looks pretty messy. Let's see if we can clean it up a bit. And actually, before I do, base times height, I need to divide this whole thing by 2. So let's see. This guy is equal to f of x sub I times delta x plus, I'm just trying to clean it up, so let me separate these guys out. F of x sub I plus 1 times delta x times a half minus f of x sub I times delta x, again, times 1/2. So hopefully you see that we've got a potato here. I'm subtracting out half of a potato. So I'm just left with 1/2 of that potato, or in this case, f of x sub I times delta x. And then I'm going to add f of x sub I plus 1 times delta x times a half. And then if we look at this, there's some additional cleaning up that we can do. We can put everybody over 2. We can factor out the delta x. And we can put f of x sub I plus f of x sub I plus 1 over in the numerator of the fraction. What a great formula. Why is that a great formula? Well, the midpoint rule, what this is doing is we are using the y value halfway between the interval. What is the trapezoid rule doing? It is literally taking the average of the y values for each interval. So in other words, for this example that we had here, I would need f of 0 plus f of 1 over 2. F of 0 plus f of 1 over 2 times my delta x, which is 1, plus f of 1 plus f of 2 over 2 times my delta x, which is once again 1. Now let me just plug these guys in here. So we get e to the 0 squared plus e to the 1 squared. I'm just plugging it into my function over 2 times 1. Plus f of 1, which is e to the 1 squared, plus e to the 2 squared over 2 times 1. So that's how the trapezoid rule works. So how do these guys relate in terms of underestimates and overestimates? Well, it turns out that the concavity of the function is going to have an effect on whether we have an underestimate or an overestimate. So the easier one to think about is the trapezoid rule. So if a function is concave up, take a look, if a function is concave up, we can see that we're going to have this straight line above the function, so that the trapezoid rule is going to be an overestimate. So if a function is concave up, and we have an integral from a to b of f of x dx, we're going to have the trapezoid rule up there. So what about the midpoint rule? Well, this one's a little bit trickier to see, I think. We'll go through it, but once we get a couple of these up here, I think it's much easier just to think of things in terms of the trapezoid rule. I'll show you what I'm talking about when we're done. So let's take a look over here. So if it's concave up, if the function is concave up, then in this case my function's increasing, and it's increasing faster and faster. So that means that if we look at just the halfway point, it looks like I'm overestimating here because my rectangle is above the curve, but then I'm vastly underestimating it here because, again, on the second part, my function's increasing faster and faster. So as a net, this is going to be underestimating the integral. Again, it's a little bit tougher, I think, to see than the trapezoid rule. So my hint in terms of remembering this is to draw a picture, get the trapezoid rule, and then the midpoint rule is going to be the other one. So in other words, from the picture, hopefully it's clear that the trapezoid rule is overestimating, therefore the midpoint rule is going to be underestimating for concave up. So what about for concave down? So what if we are concave down? So in this case, let me draw a picture. So let's say you've got from here to here, and if you drew a trapezoid, then hopefully it's clear that this guy is going to be an underestimate because we're underneath the curve. Sorry, that could have been straighter. Drawing at an angle is never advised. Better trapezoid. Okay, so once again, from this picture, we can see that we're going to underestimate using the trapezoid rule. Again, I think it's tougher to see what's going on with the midpoint rule, and therefore I think it's way easier just to use the trapezoid rule to help you see what's going on. But let's try to work this through. So this is the midpoint rule. I just took the midpoint. So over here, I'm underestimating. But concave down means that it's decreasing faster and faster. So that means I have way more stuff above the function on this side. And because of that, as a net, the midpoint rule is going to be higher on this side. So in summary, we've talked about the left sum and right sum again, and we've introduced the midpoint rule and the trapezoid rule as ways to approximate integrals. In the grand scheme of things, where is this even used? That's a great question. And this is used by computers, calculators, to actually compute integrals. So they want to try to compute integrals in the fastest manner possible, the definite integrals. And therefore, they need to choose approximating techniques which are appropriate in terms of being the way to most efficiently do the computation. All right, thanks for listening, and I hope you enjoyed this lecture.